So we're going to be talking about something that we can do to functions. We've talked about all different kinds of functions, linear functions, absolute value functions, quadratics, polynomial functions, exponential, logarithmic, reciprocal functions. The only type of function that we have left to talk about this semester is trigonometric functions. But I thought it seemed to make more sense to talk about transformations of functions first. Now, transformations of functions applies to every single function out there, okay? So it even applies to things that aren't functions, but we're gonna focus on functions, and even anything that we talk about, as I said, it applies to every other type of graph. So whatever we do with functions, you would do if it weren't a function as well. Okay, so what does it mean to transform something? So the word transform really means to change. So any of you who you might have done this when you were kids, you might even still be familiar with it. Do you remember you might have used to play with Transformers? So when I was a kid, Transformers was huge. Everybody would have Transformers at home. Where you would have the cars that would change into these robots, and they have it in the movies now, and you have young kids who get really excited by it. And what they're doing is they're changing the way that something looks. Well, that's what's happening here. We're changing the way that a function looks. So transform means to change, and that's what we're doing. Changing the way that a function looks, and there are two different ways that we could change it. We could just change where it's located. We could change how it's oriented, the orientation of it, or we could change the actual shape. Okay, so for functions, change the orientation, means, and this is the first one that we're going to be doing, but it means, like when we talked about the quadratics, that they could face up or they could face down, that would be the orientation. When we had the polynomials, right? If you think back to the end behavior where the left would rise and the right would fall, this would flip it where the left would fall and the right would rise. Okay, so we can change the orientation. We can change the location of the function, where it is on the x-axis or in the coordinate plane, or we can change the shape. If we change the shape, it's called a non-rigid transformation. So in a rigid transformation, the shape does not change. So to explain this, I want you to imagine holding like your calculator, okay? If you held your calculator, you could squeeze it as much as you want, but nothing is going to happen to it. It's very, very solid, but that doesn't mean that you can't rotate it. It doesn't mean that you can't move it around. It's just that you can't change its shape, okay? Instead, think about, let's say, a stuffed animal. So a stuffed animal you can squeeze, right? So we could take this stuffed animal here and we could squeeze it. We can change its shape. But in addition, we can move it up and down, okay? We can also rotate it. We could change the direction that it's facing. So that's the difference between rigid and non-rigid. So if it's rigid, no matter how much you squeeze it, no matter what you do to it, you're not going to change its shape, okay? So, and that would be with objects. So with transformations, what we're saying is that the thing that we're doing to it doesn't change its shape. So there are a few different types of transformations. We're going to be talking about 3 of them. So the 3 transformations that we're going to be looking at in this lecture, we're going to look only at reflection. But we're also going to look at translation and dilation. So in this lecture, we're going to focus on reflection. There will be 3 videos for this unit, 1 on each type of transformation. Some of you might also be familiar with rotation. If you remember doing transformations just with points, you can also rotate. Okay, you can rotate an image, but we're not going to do rotations of functions. We're only going to do reflections, translations, and dilations. And if you think about reflection would be as if you took the image and you reflected it in a mirror, okay, where a line on the coordinate plane represents one of those mirrors. So we'll talk about that a lot more. But essentially, when you look at yourself in the mirror, you're not changing your shape unless it's a really special type of mirror. You look the same, okay? It's just that you're changing your orientation, okay? So reflection is rigid, and it changes the orientation. This is where it might change, whether it's facing left or right or up or down. Reflection changes orientation. Translation is also rigid, because translation, to translate something, actually means to move it. So this changes location. And then finally, dilation is non-rigid, because when you dilate, you're making it larger or smaller. Okay, so think about your pupils dilating. When they dilate your pupils, if you've ever went to the eye doctor and they've dilated your pupils, what they're doing is they're making them larger. Okay, so dilation is non-rigid, because in this one, it's changing the shape. Okay, so let's talk about reflection. So there are 3 different kinds of reflection. And again, remember I said reflection is where we use a line or actually even a point as a mirror. Okay, so we already talked about one of these. We talked about the fact that the inverse of a function is its reflection in y equals x. So let's take an example so that you can see that. I'm going to turn that off. Let's do e to the x, and let's do the ln of x. Okay, and we'll put in the line of reflection. So these are inverse functions, right? E to the x is exponential. The ln of x is logarithmic. We know that these are inverse functions. We talked about that when we introduced logarithmic functions earlier. And we said the inverse of a reflection, the inverse of a function is its reflection in the line y equals x. So you could picture standing on this point, facing the line y equals x at a perpendicular angle, okay, at a 90-degree angle. And if you look at, let's say, this distance here, it looks like it's about 1 unit. We're not being exact, but it's about 1 unit. And the corresponding point on the other function is also about 1 unit away if you're facing the same direction. So this line y equals x is acting like a mirror, okay? If you were to stand over here, let's say, and face the line, you're this distance away, and then you can find your corresponding point on the other function on the other side of our line, of our line of reflection, okay? So you can see that this y equals x is a line of reflection here. So we're not going to talk that much about reflection in the line y equals x. That's just inverse. But that's the first line the first type of reflection that we actually talk about. So this is just a reminder that a reflection of a function in the line y equals x is its inverse. And because we don't want to be contradictory, we're going to put as long as it's a one-to-one function. If it's not a one-to-one function, then it just wouldn't be called an inverse, but you would reflect it in the same way. So if you remember, we switched the y and the x. Just switch x and y and solve for y. But again, we're not really talking about this. This is just a reminder. We're going to talk about the others, okay? So the 3 other types of reflection are a reflection in the x-axis, a reflection in the y-axis, and then actually a reflection in a point, a reflection in the origin, okay? What this is saying is the y-axis acts as a mirror, the x-axis acts as a mirror, and the origin, when we say that we're reflecting in the origin, what we're saying is picture almost like a circular mirror. There's the mirror all the way around the origin. Okay, so picture, think of it as you are, it's like cylindrical, okay, where the cylinder, there's a mirror all on the outside. So here's your cylinder. Imagine that this whole black area is a mirror. Okay, here's your cylinder. Imagine that this whole area is a mirror here, okay? So wherever you stand around this mirror, you can see your reflection that goes right through it to the other side, okay? Okay, so let's start with a reflection in the y-axis. I wrote it first, so let's start with that. The way that we write this, and you might see it abbreviated in slightly different ways in different textbooks. Sometimes you'll see it with a small r, sometimes you'll see it with a large r. But I'll abbreviate it like this, okay? A reflection in the y-axis here. So in order to do this, let's take a look at a single point and see what a reflection in the y-axis is for a single point, because that will inform what a reflection in the y-axis is for a whole function. So we can draw our axis. We know we're using the xy coordinate plane here. So let's take one point, and what we'll do is we'll call it 3, 6, okay? And what we're gonna do is we're gonna say, okay, well, what is its reflection in the y-axis? Well, the reflection in the y-axis would essentially say, okay, stand on this point, face the y-axis, okay? And when we say face the y-axis, we're saying at a perpendicular, okay? Be perpendicular to it. So don't face it at an angle. Don't face it like this. You're looking directly at it, okay? So you're standing, you want to see your body full front, okay? You don't want to see yourself at some sort of an angle. So if we do that, okay, right? We're standing like this and we're facing it. And what we want is we want to see our reflection on the other side, which means that this distance to the y-axis here is going to be exactly the same as our distance to the y-axis on the other side. So on the other side, we have our reflection. And we're saying, okay, well, what is the coordinates? What are the coordinates of that new point? Okay, well, we're at the same height, so our y value remains the same. Our y value is still 6, because we're still 6 units from the x-axis. But our x value changes. Our x value, instead of being positive 3,6, it's going to be negative 3,6. That's our new point. So let's generalize this then. Let's say that we have any point, x comma y. So it doesn't matter where it is on the axis. So I'm putting it down here because it makes no difference. And we do exactly the same thing. We're standing on this point, facing the y-axis, and here's our new point. And we're saying, okay, well, what are the coordinates of that new point? Well, the x is changing sign. So it becomes negative x. The y is the same. Okay? And the same thing would be true if we started on the other side, right? If we started on the other side, and this was our point, x comma y. So notice x comma y can represent any point, okay? Then if we find its reflection, the fact that x is negative here doesn't make a difference, because what's happening is that when we get to our new point, whatever our original x was, our new x is the negative of that. So if this is negative 10, then this is the negative of negative 10, which makes it positive. So this is still negative x comma y. Okay. So what we're seeing is, to reflect in the line y equals x, not y equals x, to reflect in the y-axis. Sorry about that. You keep y the same, and change the sign of x. Okay, so here's what this means for functions. The reason why we looked at coordinates first is because that tells us what to do with the function. So I'm going to remind you that in a function, when we have f of x, right? X is our input. This is our x value. That seems pretty clear. But f of x altogether, f of x altogether is our y value, or our output. So we can use the reflection in the y-axis with points to inform us about what to do with the function. So for a reflection in the y-axis, x comma y becomes negative x comma y. So what this tells us is that f of x becomes f of negative x. All our x values become negative. Or I should say, no, become negative. So let's take some examples so that we understand what this means, okay? So we're going to take a bunch of different functions and just reflect them in the y-axis. So let's say that we have f of x is equal to x squared plus 1. Okay. Well, what this means is that f of negative x, the reflection in the y-axis, f of negative x is negative x squared plus 1. And here's the thing though, right? What is negative x squared? Negative x squared is just x squared. So if we go in and we graph this, we can get rid of these for now. If we go in and we graph x squared plus 1, this is what the function looks like. Well, if we graph the reflection in the y-axis, you can see it's exactly the same. When we're reflecting in the y-axis, you're thinking of it like almost like a line of symmetry. Every point on this side, their reflection is over here, and every point on this side, their reflection is over here. So it actually reflects onto itself, okay? Let's take a different function though, one where that won't happen. Let's say that we have f of x is equal to x plus 8 squared. I'm going to change the color. I'm not changing what I'm writing, just changing the color so that we're consistent. So once again, we're going to reflect this in the y-axis. Which means that every time that we see an x, we're changing it to a negative x. So instead of x plus 8, we have negative x plus 8. Okay, so this is just like composition of functions that we did way back when. Okay, so again, let's take a look at this graph. You're not going to see it right away. So you see it, so we have x plus 8, and let's change this. This becomes negative x plus 8 squared. you can see that these are reflections of each other in the y-axis, right? The y-axis is acting like a mirror for these two functions. This point right here, its reflection is on this side over here. This point right here, its reflection is on this side right here. This point right here is that x equals -8. This point right here is that x equals +8. Okay, let's take a few more. Let's take some different ones. Some of these, we might not know its exact location on the axis, so if we graph it, we may or may not be able to see it. So we're just going to take a whole bunch. We have f of x. Let's do a polynomial function. Let's say that we have x cubed minus 6x plus 1. Okay. We'll do f of x is equal to 2 to the x plus 3. So we'll do an exponential and we'll do a logarithmic. F of x is equal to log of 6x minus 4. And let's also do a reciprocal function. X plus 2 over x squared minus 6. Okay, and for each of these, we'll find the reflection in the y-axis. So again, all we're doing is we're replacing all of our x's with negative x's. So don't forget about your parentheses, right? It's x cubed. This becomes negative x cubed minus 6 times negative x plus 1. You can simplify this, okay? If you simplify this, you get negative x cubed plus 6x plus 1. Sometimes it'll be helpful to simplify, sometimes it won't be necessary, okay? Okay. For our next one, again, all we're doing is we're replacing the x with a negative x. So this x here just becomes negative, so it becomes 2 to the negative x plus 3. When do you need parentheses? That would be a typical question. You need parentheses if you're raising your x to an exponent. If you're doing something to the x, okay, other than adding or subtracting, then you have to put parentheses around it. If you're not sure, you're never wrong if you put the parentheses around it. Negative x plus 3 is the same thing as if we put parentheses around the negative x. Okay, so that's another way of really keeping track of this, is you could put parentheses around each of your x's and then replace what is in the parentheses with a negative x in the corresponding function. Okay. Here, our f of negative x is log. And then we have 6, and we need the parentheses here because otherwise it's going to look like 6 minus x, right? And again, I just want to be consistent with the colors. Okay, again, we need parentheses in this one because if we don't have them, it's going to look like 6 minus x, and we need it to be 6 times negative x. And if you want, you can just go straight to negative 6x. Right? 6 times negative x is negative 6x minus 4. And then for this one, be aware there's more than one x. Every x needs to be switched. So this becomes negative x plus 2 over negative x squared minus 6. And if we were to simplify this, and again, you won't always be asked to simplify, but you should know how to do it. Negative x squared is just x squared. Okay. And let's just graph some of these functions. Okay. So let's take, we won't do them all, but just so that you get some idea. Let's do 2 to the x plus 3. And then we'll do 2 to the negative x plus 3. And you can see the y-axis is clearly a reflection here. This crosses, the black one crosses the y-axis, so the red one will also cross the y-axis, okay? But this y-axis is a line of symmetry between the two functions. Let's try the reciprocal and see if we could see it. Let's do x plus 2 divided by x squared minus 6. Okay, so we could see what the function is in blue. Now let's take its reciprocal. It's reflection. And so it would be negative x plus 2 divided by, and I'll put the negative x squared plus 6. I'll do it without the simplification. And it's a little harder to see, right? But it actually is a reflection. Let's look at them separately. Okay. So everything you're going to have with green. So for this part, you're going to have green on the other side. It's just going to point this way. Okay. And let's close this and magnify this a little bit. So here you can see it a little bit more clearly, right? That here's the green. This middle green piece is reflected by this middle blue piece. This green section of the graph, its reflection is over here in the blue section. And then this section here, here's the reflection on the other side. So we can see that each of these functions gets reflected in the y-axis. Okay, so that's the y-axis. So the x-axis is really not any different than the y-axis. It's just that it's using the x-axis as a line of symmetry. So we're going to start the same way that we started with the other one. We're going to look at the coordinates first. So the difference is that here our x-axis is our line of reflection. So if we take a point, let's take the point 1,7. Okay. Now the difference is because the x-axis is the line of reflection here. Instead of standing on our point and facing the x-axis and facing the y-axis, we're going to stand on our point and turn towards the x-axis. Okay. And if we turn towards the x-axis, we're going to be the same distance, but on the other side. And if we look at our new point, well, this time we're still to the right by 1. We haven't changed that. That part is the same. But now instead of being at 1,7, we're at 1,-7. So the difference is that instead of our x changing like it did here, right? Our x changed because it was horizontal. Now we're doing a vertical. We're vertically affecting our graph, right? This is a vertical change because our point is moving down. And that means that we're affecting the y. So, and this is something that you're going to see with all of the transformations. If you're doing some sort of vertical change, you're changing the y values. If you're doing a horizontal change, you're affecting the x values. And I'll write that in a minute, but let's finish just generalizing this. Let's say that we take another point, x comma y. Well, if we reflect this, the same thing happens. You're facing towards the x-axis, and then you're going to be an equal distance on the other side. So what's our new point? X comma negative y. And then again, it doesn't matter what side of the x-axis you're on. These things always stay the same, right? If our y starts off as negative, that's okay. So we still call this point x comma y. It's just our y is negative. And if we go to the other side of the x-axis, we're still just changing sign here. This is still just x negative y. So what we're saying here is that for any given point, x comma y, if we want to reflect it in the x-axis, it just becomes x comma negative y. So we can generalize. So I just want to write down what we said a minute ago, that any horizontal change will change the x values. So, for example, a reflection in the y-axis changed the x to negative x. And any vertical change shouldn't be a comma here. We'll change the y values. And in this case, what that means is, instead of just saying the y to negative y, because we're working with functions, we're going to say the f of x to negative f of x. Because remember, f of x is y. And this statement is true for every single transformation. And this will help you keep straight what you're supposed to do. Okay, so let's go back to this reflection in the x-axis and do examples, just like we did with the reflection in the y-axis. So we know that our x comma y is now x comma negative y. And what that means with respect to f of x is that our whole y value becomes negative. Our whole function becomes negative. So I'm going to list the exact same functions that we had before. And we'll see how they look different when they're reflected in the in the x-axis instead of in the y-axis. So we had f of x equals x squared plus 1. F of x equals x plus 8 squared. F of x equals x cubed minus 6x plus 1. F of x equals 2 to the x plus 3. And notice again, we're doing all sorts of functions. I'm trying to include every type of function that we've looked at. I'll even add an absolute value in here, just so that you see it. We'll add in f of x equals absolute value of 2x minus 4. So these are all different types of functions. And let's take a look at what happens. Okay? So now we're reflecting in the x-axis. Okay? And notice what this means. This means take your function and put a negative in front of it. So this whole side over here is f of x. So it's saying take all of this and put a negative in front of it. Okay. This we can simplify. This becomes negative x squared minus 1 if we distribute. Okay. And if we go into our graph again, I'll leave these here for later because we might want it. Let's take our x squared plus 1. And what we're going to do is we're going to reflect it in the x-axis. So we're putting a negative in front of the whole thing. Okay. And what do we see here? We see a reflection in the x-axis. So now for every point up here, there's a corresponding point down here. We can do that for all of these. So in this one, again, the negative goes in front of the whole function. So we don't need parentheses around this because it makes no difference. But again, if you want to, just put parentheses around the whole function like we did up here and put a negative in front of it. It turns out that it doesn't change anything because you do the square first no matter what. Okay? It just, what it means is you can't distribute this negative because you have to square first. Okay? And that's not going to change. And once again, let's do this one. We're not going to graph all of them. But this was x plus 8 squared. And now we're going to do negative x plus 8 squared. And you can see here, again, it's a reflection in the x-axis. Okay. Let's do these other ones. So again, negative f of x. And you just put a negative in front of the whole thing. You have to put a negative in front of the whole function. Okay. You can distribute it, but you're changing the whole function. This one, a negative in front of the whole function. So when do you need parentheses? It has to do with the order of operations. If the parentheses are not going to change the order of operations, then you don't need them, okay? So a 2 to the x plus 3, multiplying the whole thing by negative, you still have to do the x plus 3 first. And this doesn't change that. You would still have to do the x plus 3 first. Here, if you didn't have the parentheses, then you would only be multiplying the x cubed by a negative. So if it's going to change the order of operations, then you need to put parentheses. If you're not sure, put parentheses in there. You can't go wrong. The last thing that you do should be to multiply by that negative. That should be the last thing, not the first thing, which is what it would be up here without parentheses. Without parentheses, the negative is going to come before the subtraction and the addition here. You don't want that. The subtraction, this whole thing, has to come before multiplying by the negative. It doesn't make a difference for log. For this function, you could just put the negative in front of the whole fraction, and then you don't have to worry about parentheses. But again, it's got to be really clear that it's in front of the whole fraction. If you feel like it's not, put the parentheses in there. And then this one, the negative goes outside of the absolute value. Okay, let's take a look at what that looks like. We have absolute value of 2x minus 4. And then we're going to do negative the absolute value of 2x minus 4. And you can see these are reflections of each other. We can also do this one. And if we put this one in, you can see it is a reflection in the x-axis. And if you're not sure, you could look at individual points, right? This point has a corresponding point on the other side of the x-axis. That's on the blue graph, okay? And that's a reflection in the x-axis. So the next and the final type is a reflection in the origin, okay? So, and let's look at what that would look like with respect to points, just like we did with the others. And remember, just in case you forgot the terminology, the origin is the point 0, 0. And what this is saying is that your mirror is on that point. And again, we'll do it by looking at the graph first. Okay, so we're going to look at coordinates. So here's our point. Let's call this point 2, 3. Okay. Okay, so in this case, the origin is your mirror. So if the origin is the mirror, what you're doing is you're standing on the point 2, 3, and you're facing the origin. And it's a single point, so there's no like perpendicular or anything. You're just facing the origin here. And you're going to be on the opposite side, equidistant away. Well, that means that this distance is the same. So this distance is the same. But one is positive and one is negative. So this is going to be a -2. And the same thing is true about the y values. So that was the y values I was just talking about. So the same thing is true for both the x and the y, right? The distance here is the same over here as the distance here. So the x that was positive here is now negative. The y that was positive here is now negative. Okay. And this one is a little bit, I'll do another one. let's take this point over here, okay? So if we want to reflect that, this is our x comma y. We face the origin, and then we go the same distance on the other side. So this would be negative x, negative y. Both things are changing. And the same thing is true if we're in a different place. So if we're over here, if this is our x comma y, okay, then our reflection is also negative x, negative y. We're just shifting, we're changing the sign of both of them. And here it's a vertical change, right? We're changing something vertically, but we're also changing it horizontally, which means that we're affecting both the x and the y. So here's what this means. This means x comma y becomes negative x comma negative y. And what does that mean for our function notation? F of x becomes negative f of negative x. So we have to do both, okay? So let's take a whole bunch of functions. Let's do the same ones. This is a little bit longer in terms of converting them, because we're doing two things at once. And we'll do this in a couple of different, we can use a few different methods. Value function as well. Okay. So there's something I want you to notice. We're doing both. So what we're saying is we're saying a reflection in the origin is equivalent to a reflection in the x-axis and a reflection in the y-axis. We're doing both things. The order doesn't matter, right? Which we make negative first. If we make the x negative first or the y negative first, it doesn't make a difference, right? We still wind up with negative x, negative y. It's kind of like saying, I could have rewritten this point as negative 2, negative 3, or I could have written the negative 3 first, meaning negative 2, negative 3, but the negative 3 I could have written down first and then put the negative 2 in front of it. That's really what we're saying here. Okay, so in terms of the order in which we do it doesn't matter. Okay, so we reflect in the origin. A reflection in the origin is equivalent to a reflection in the x-axis and a reflection in the y-axis. So just to make what I said clearer, what we're saying is we're taking x, y, and we can reflect it in the x-axis first, which would make it x comma negative y. And then we could take this point and reflect it in the y-axis. And now we get negative x, negative y. Or we could take x comma y, reflect it in the y first to get negative xy, and then take that point and reflect it in the x. We're saying it's the equivalent. So this was reflecting it in the x-axis, and then taking that and reflecting in the y-axis. And that will give us a reflection in the origin. Or we could do this one as a reflection in the y-axis first, and then reflect in the x-axis. In both cases, we wind up with a reflection in the origin. That's what we mean by the order doesn't matter. Okay, so let's do this. So we're going to reflect this in the origin. So we can do it all at once, or we can do it one at a time. Let's start by doing it one at a time. So you can do it all at once. You can do negative f of negative x if you're really comfortable with this, okay? I'm going to do negative f of x first, and then take that and reflect it, okay? So negative f of x is equal to negative times x squared plus 1. So negative f of negative x is equal to negative, and then we're going to take the negative x squared plus 1. Okay. Now this is a case where it might be more helpful to you to distribute this negative first and then replace the x with the negative x. Okay, but this is what it looks like. This one, if we reflect in the origin, let's do this one differently. Let's do f of negative x first. We get negative x plus 8 squared, and then negative f of negative x is negative of negative x plus 8 squared. Okay, and again, it might be helpful just to say, okay, this is really just negative x plus 8. Let's do this one, but let's do it both at the same time. So we're going to have a negative in front of the whole thing. And now each of our x's is going to be replaced with a negative x. And for many of you, this is going to be the easier way to do it. To just do it all at once. Take a negative, open parentheses, because your whole function is going to go in there, and then every time you see an x, replace it with a negative x. Put a negative, open parentheses. Now you're going to put your function. Every time that you see an x, you replace it with a negative x. Okay. This is an example where you don't need the parentheses around the 2 to the negative x plus 3, but put them there. There's nothing wrong with that. Another case where you're not going to need the parentheses, it's up to you. You're putting a negative, and then every x gets replaced with a negative x. Here, you don't need the parentheses here as long as you're clear that the negative is in front of the fraction. But we're going to put them in just because sometimes it's not clear. Okay. we put the negative open parentheses because the whole function is being negated, and then every x becomes negative. So you can do this in 2 steps or 1. It's completely up to you. And then same thing here. You don't need a parentheses because the absolute value sign acts as the parentheses. So you put in negative. And then every x gets replaced by negative x. Okay. So let's just take a look at some of these. Let's take this one, right? Because it's here. So we're doing 2 things. This is our reflection, but now we're going to replace our x's with negative x's as well. And this one, it's a little harder to see. Right? It's a little harder to see that it's a reflection in the origin. It's not going to be as clear. This one isn't a great one to choose. But essentially what you're doing is you're saying this point here, its reflection in the origin is actually over here. Let's take the absolute value one. I think it's going to be clearer than the reciprocal function. Let's take absolute value of 2x minus 4. And then we're going to do negative absolute value of 2 times negative x minus 4. Okay. This is a reflection in the origin here. Okay. You can see this point, its reflection is 2, 0. Okay. If you took this, so imagine, let's also reflect this just in the x-axis. So you can see that this middle one, this blue one, is a reflection in the x. So we took the black, we reflect in the x, and then we take that reflection and we reflect in the y, and we get the reflection in the origin as a result. Okay. Let's take the x squared plus 1. Now, if you reflect in the y-axis, nothing changes. So a reflection in the y and then a reflection in the x, you wind up with exactly, it's just a reflection in the x, right? Because a reflection in the y doesn't change anything. And we'll actually talk about that in a minute, what happens when that happens. Let's take that 2 to the x plus 3. So if we have 2 to the x plus 3, and we reflect it, this is what it looks like as a reflection in the origin. You can see here, these are points that are reflections of each other. Let's take the x cubed minus 6x plus 1, just so that you see lots of different functions. And you can always do this yourself, because you have access to Desmos. I think they even have an app if you're just using your phone. Okay. So we're going to do both. So think about it. So I'm actually going to do a reflection in the x first. Okay. This is a reflection in the x, and I want you to notice I want you to think about what you think might happen when we reflect in the y as well. So notice every x is getting replaced with a negative x. Okay, so this is the green function. So you can see that you have the red function, right? We reflect it, we get the blue, that's reflecting. Let's close this so that you could see it better. Okay, so we took the red, we reflected it in the x, which means that we turned it upside down and we got the blue. upside down, we got the blue. You can see this, that the red is exactly opposite the blue. Then we took the blue and we reflected it in the Y to get the green, okay? And if we take out this middle blue one, this is what it looks like when it's reflected in the origin. So it looks really different, right? In the sense that it doesn't look like it would be a reflection in the origin, and yet it is, okay? Let's take one more. Let's take the x plus 8 squared. Just so that you get used to seeing these different functions. And here's another reflection in the origin, okay? And if we reflected this in the x and then we reflected in the y, it would look just like this. So this is a reflection in the origin. So there's one last thing about reflections. And that thing is, for numbers, we have even and odd numbers. For functions, we actually have even and odd functions. And not every function is even or odd, just like not every number is even or odd, right? We have 1.2, that's not even or odd. So in functions, we have the same thing. We have some functions that are even, some functions that are odd. An even function is when the function is the same when we reflect it in the origin. In the y-axis. I got ahead of myself. In other words, f of x is equal to f of negative x. So, examples of even functions. Easiest example, f of x is equal to x squared. If f of x equals x squared, f of negative x is equal to, in parentheses, negative x squared, okay? What happens when you square a negative number? It becomes positive. For the same reason, f of x equals x squared plus 3. Well, f of negative x, which is a reflection in the y-axis, remember you're thinking about a vertical change, so when there's a horizontal change when we reflect in the y-axis, right? You're going from here to here. So that means that we're affecting our x values. So this becomes negative x squared plus 3. And what's negative x squared? X squared plus 3. The same thing would be true of any function where you have x raised to an even power. Negative x to the fourth is just x to the fourth. Okay. Another example, if we look at it graphically, would be any function where the y-axis is a line of symmetry. So in other words, if we have a function like this, y-axis is a line of symmetry. So because of that, every point that's on the right over here will have an equivalent point on the any function. This would be another one. So any function. With the y-axis as a line of symmetry is even. And graphically we saw this. Not with this one. But with x squared plus 1. Took this and we reflected it in the y-axis. You can see the blue and the red are on top of each other. Okay, this is indicative that it's even. Then we also have odd functions. So an odd function is when the function is the same when we reflect it in the origin. So, for example, what we're saying is f of x equals negative f of negative x. So, for example, I don't have a lot of examples when it comes to graphing, but if you have f of x is equal to x cubed, okay? Negative f of negative x negative of negative x cubed, right? So we put a negative in front of the whole function, and then we change the x to a negative. Well, negative x cubed is negative x cubed. This inside, it simplifies to a negative x cubed where you don't need the negative x in parentheses. And then negative of negative is positive. It's the same function, okay? When we look at graphs, this would be an example. That was not well drawn. In other words, what you see here, you're going to see what you see in one quadrant, you're going to see in the opposite quadrant, but upside down essentially. Okay, think about it as if we reflect this in the x and then we reflect it in the y, it's going to look exactly the same. Okay, let's see if I can try and do one more. This would be another example. If we reflect it in the x and then we reflect it in the y, it looks the same. So let's just see. Let's just do this last one. X cubed. Here's what x cubed looks like. You should be familiar with that, right? It's an odd degree, so the two sides are doing different things. When we talk about end behavior coefficient is positive, so the positive side is rising, right rises, the left falls. exactly the same graph. So these are odd and even. Now, if you notice, we talk about an even function when the function is the same when we reflect it in the y-axis. Odd is it's the same when we reflect it in the in the origin. So what happens when we reflect it in the x-axis? Is it the same? Well, here's the thing. If you can reflect a function in the x-axis, you're saying that the x-axis is a line of symmetry. If the x-axis is a line of symmetry, it's not a function. Okay? So let's just make a note of that. A function will never be the same when you reflect it in the x-axis because that would mean the x-axis is a line of symmetry. Then it wouldn't be a function. Right? It fails the vertical line test. Here's an example of a function. Here's an example of a graph where the x-axis is a line of symmetry. It fails the vertical line test. Here, what we're saying, what we are saying, we haven't really talked about this that much, but what we are saying is that this is any function with the origin as a point of symmetry. Okay, so we don't talk about the x-axis being a line of symmetry because that's not possible if it's a function. If it's a function, the x-axis would not be a point of symmetry. And that is it for reflection. So translation we'll do next time, and then for the last lecture, we'll do dilation.